we are trying to derive an expression for the shear stresses in a beam. Earlier, we derived the expression for normal stresses in a beam. And so consider a beam. Yeah. Yeah. Shear stress tau. Okay, so assume that it's has some kind of load on it. Xy. And just like before, let me draw the cross section too. So the cross section will look like this. This is Y. So X goes in the plane of paper, so C should be this way. So like before, what we do is we consider a small element on the beam. And I'll blow it up. Let's call the site some names, C prime, D prime. Sigma, say sigma C, sigma D. So delta H is the net horizontal force, which is, think of that like the force which will shear that element, right? But it doesn't shear because it's held in place by something which is opposing it below it. So let's say that this is our neutral axis. And when I drew this element, it was at a distance of y from the neutral axis. This distance is, I'll just call it y1, and reserve y to be the distance of any horizontal element from the neutral axis. C. And then if you draw the cross section of the same element, this is the side view. Cross section. This area is dA since it's a small element, and then this distance is again be the same y. It's y1, but this is y1. Then we are interested in some distance somewhere on that plane stress element, the distance y. And then the other dimension I want to have over here is the width of this section. Let's say that the width is b. Okay, with this, we're all set to figure out what the shear stress is. Okay, so delta H is the force to face C prime D prime. So it's sort of like a force which shears the C prime D prime from the rest of the beam. So we can do equilibrium of forces in the x direction equals 0, which gives me delta H, which is the force acting to the right. Okay, sigma C is some kind of a normal stress which is acting on the face CC prime. So the cross-section area for CC prime, you can see it from the side view, it's dA. And since we're interested in the complete force, we will need to integrate this. I'll put the limits in a bit. And then this would be positive because it's acting to the right. And then similarly, there is sigma d, which is the stress, normal stress on face d, d prime, acting over the cross-section area dA. We need to integrate that. And since it's acting from right to left, the negative sign. Okay, so we can move things around. Close. Integral sigma d minus sigma c. Yeah. But we know that sigma, which is normal stress, something we did in the previous section, sigma equals moment times y divided by I. So I'm just going to substitute sigma as so, but replace sigma d with, there's a moment md acting say on the left and mc on the left, md on the right. So I just have to replace the right stress there. So I'm going to do that. Put this up, we get md sigma d minus mc, and then there is d. Okay, remember that delta H was the stress on the lower end, which can also be written as the shear stress. Okay, and then this shear stress acts let's see, the cross section was A, B. If you will, you can draw this like this. Since this is B, this is the cross-sectional view, this is going to be B. Right, this is the same as this. And then since this length is along the x-axis, that's dx. So the shear stress is acting over the bottom face, and the bottom face has a, in this case, the thickness of B and length of dx. So that's going to be the shear force. That will be the cross-section area over which the shear force acts. So force is stress times area. And so what I'm going to do is take this and sub it in this formula. We almost did with the derivation. So we have T B dx equals integral md minus mc by I dA. So this is the net moment which acts between the left half and the right half, and I can sub that as dm because that force is a very small moment, which is the difference in the moments in the left and right, and that element is very small, so it's dm. And so I can pull this dm out because that dm doesn't really integrate in this, so it's a constant. dB dx equals dm. I is a constant. I can pull that out. So I'm left with y dA. And so tau divided throughout by b dx. We get 1 divided by I times b dm dx, and then y d. Okay, that is the formula for shear stress. Turns out that you normally see it in slightly different form in the books. You see it as tau equals 1 divided by IB. We know that dm dx. What's dm dx? Shear force, so it's V. And then people like to call this integral y dA as, is there a name for it? It's called Q. It's an abbreviation it's normally used. It's the first moment, area moment, as they call it. It's called area moment because there's area dA, and y signifies the sort of the moment arm. Better way to write this is BQ now. When you compute Q, what you need to do is the neutral axis. This was y. This is the lower limit, let's say y1. This is the upper limit c. So you basically integrate from y1 to c. Okay, that is, we are interested, if you're interested in finding the shear stress here, at some horizontal section, you integrate from the lower end, wherever you're going to find, all the way to the topmost part of the beam. Because it's because the shear force experienced by that plane, the one shown in blue, is due to what is sitting on top of it. Tau, the transverse shear stress. Yeah, question. Here. Okay, so here's the important thing, which is something you want to remember, and this is a common mistake people make. If you look at this formula, tau equals VQ IB, where Q equals integral y1 c y dA. I just wrote down the same formula from the previous page. That's my element. That's the topmost part. Just blow it up a little bit. Okay, so this is the neutral axis. on the neutral axis, you can see that y1 equals c, right? And so q, sorry, my bad. What am I doing? Y1 is 0, right? My bad. So we have q equals integral 0 to c y dA, which is not equal to 0. It's some value. It's so tau is actually maximum. It's maximum because y dA is maximum when you integrate from 0 all the way to c. On the top edge, y1 would be c, and q would be integral c to c y dA, which will be 0. So tau is equal to 0. So shear stress is maximum at the neutral axis, and it's 0 on the top edge. Okay, this is exactly opposite to what we've seen for bending moment M, normal stress. This is the reverse of what we have seen for sigma, right? Where sigma equals sigma max at the edges and sigma equals 0 on the neutral axis. Remember, we drew this figure showing the stresses for normal stresses. 0 on the neutral axis, but it's compressive on one side, and then it's tensile on the other. No. Sigma, I mean, just depends on how you choose the sign of which side you want to call positive, but it's going to be some non-zero value at the edges, which is opposite to that of shear stress. Okay, and this is a common mistake people make, which is in the exam I've seen when you're asked to solve for stresses, we'll just assume that the normal stress would be maximum. But they make the mistake normally with the shear stress. They say that the shear stress is going to be maximum at the top edges, which is not true. In fact, the shear stress is always 0 at the edges because there's nothing to shear over. But for normal stress, it's a very different mechanism. It's basically the stretching and compression. And since the stretching is the maximum at the edges, you'll see that the normal stress is maximum at the edges. So given this information about the stress, the shear stress, we can actually compute the stress in whatever geometry you want by just taking that formula. B is known, I is you can find as a table, B is the width, Q is the one which you need to integrate. So you need to give some information about how Y changes with cross-section area, and then you can integrate that equation to find Q. And once you find Q, you can find the shear stress. So I'm not going to go through the derivation of these things, but there is a table in the book. So it basically gives you the values for the maximum maximum stress and average stress. So if you have a, for example, a rectangular section, then it again shows you how the shape of the transverse shear stress would be. It's maximum at the middle and then tapers down and goes to zero at the edges. Then this is a annulus. It's a little bit more steeper than the other one. So this one is actually quadratic, and that one I believe is probably a third order or something like that. That's why it's this shape. And this is for a circle, and that's for a flange. And so you will probably be given this formula, tau max, and then you can use this formulas to find the maximum stress. Now, when they say tau max, that's the stress at the middle. And then if you want to find average, it's going to be V divided by A. But that's something which you can derive from that formula I wrote down or rely on the table. Okay, so let's see how to apply some of these things into to problems. Okay, I actually posted this on the handouts tab in Blackboard. If you're not taken it, you can, if you want, you can copy it. Or it'll be available as notes in the lectures. The beam is simply supported and loaded as shown. The beam is made up of 3 plates. So this is plate 1, probably plate 2, and then plate 3. With 2 joints. So the joints are clearly here and here. The width of the beam is 20 mm. Where is that? Okay, this is the one, 20 mm. And the location of the center of the section is at C. Okay, that's, well, it's kind of obvious. It's going to be at the middle of the beam, of the vertical beam. And the central moment of inertia is 8.63 times 10 raised to negative 6 meter raised to 4. Find the average shearing stresses at the joint A and B at section NN. Here. In section. Okay, so before we solve this, just one note that you're given the centroidal moment of inertia, but if you're not given that, you should be able to compute it from that from the cross section, the top from the bottom figure. We've done this in the moment normal stress section, right? What the way you'll do it is you'll consider it as 3 pieces. You want to find the inertia about C. So let's call this 1, this 2, and this 3. Then I of C would be inertia of 1 plus inertia of 2 plus you'll have to do area times, call this R2. It's the distance to the centroid. Call this distance R3. So then you'll have to use the parallel axis theorem and compute area 2 times R2 square. That would be the inertia of section of the area 2 about the centroidal axis C. And then you do the same thing for 3. Okay, so that is if you're not given the centroidal moment of inertia, you'll have to do that calculation yourself. Okay, anyway, this is doing. So let's proceed to solve it. Clearly, this is a problem involving shear stresses. We need to find the stresses. First of all, we need to find the stresses here, but it's at this section. So what is the section to do with finding the stresses? We need to find the shear force, V. Unless we find the shear force, the formula is VQ divided by IB. This has to be at section NN, right? Q will depend on, so let's call this figure A, P. So we will use figure A. That is, we'll draw a shear force diagram in order to find the shear force. That's how we'll get B. Q will come from looking at B, and these parameters also come from looking at B. So we need the shear force or the free body diagram and so on to find V. And then we can proceed with the other parts. So this is where you can see how what we learned previously, the previous section of what was there in the exam about computing the shear force is important. Okay, so let's first find the shear force at section NN. So just draw a shear force diagram. And then we can use the formulas we learned in this section to solve for shear stress. Okay, let's start with the free body diagram for the beam. So on the left side, there was a pin joint. So B, and let's call that A. That was A, VA, HA. And on the right side, there was a roller. So VB, no horizontal force. And right at 0.4 meters from the left, there was a force of 1.5 kilonewtons, and then there was a force of 1.5 kilonewtons to, I think, 0.4 meters to the right of P. These dimensions are going to not to scale 0.4. You can use the equilibrium equations. Summation of forces in x equals 0, y equals 0, and then take moments about A and B. But really, there's a shortcut to this problem. Because the forces are symmetric, it has to be, and by symmetric, I mean they are 0.4 meters from the reaction points A and B. VA and VB have to be equal, and they have to be 1.5 kilonewtons, otherwise this thing is not going to be in equilibrium, right? So we can take a shortcut here. So HA is 0. VA equals VB equals 1.5 kilonewtons. Because the loading is symmetric. So NN was here. So we need to find basically the shear force between A and the first load. Okay, now you can draw the shear force diagram, but really you're not asked to find the shear forces at every single location. So drawing the shear force diagram is probably not very optimum, right? You only want to find the shear force at section NN. So instead of drawing the shear force diagram, we'll just take that section from A to NN, show the forces, and compute V. This is something which we did a long time back, right? To find the shear forces. So we'll not draw the shear force diagram because it's not asked. So let's cut the beam exactly at NN. Show the forces, 1.5 kilonewtons. There is a shear force acting downwards. The convention for this cuts is that downwards shear force, when the section is cut from the left, is positive. And so minus 1.5 plus V equals 0. And so V equals 1.5 kilonewton. Okay, so that's the shear force which we were after. Okay, now the first question asks us, we need to find the average shearing stress at joint C and joint B. That is right here and right there. Okay, so let's let's develop the formula first. And once we develop the formula, we can figure out what dimensions we need over there to solve this. The top beam, this is joint A. Okay, so the formula we want is shear stress at joint A is VQ divided by I times B. Okay, V is known, it's 1.5. I is the inertia is always about the centroidal axis, which is given to us. Okay, now Q and B are the unknowns. So we are interested in the average shear stress. Right? So Q is integral y dA. So it's the first moment of the area. And so what we need to do is we need to find the first moment of this beam from the neutral axis. So for a shape which is regular, this formula is the geometric center times the area. So that area is the cross-section area, which I've shown in that figure. Yeah. Oh, so that's given to us. It's yeah, C. Yeah, the C is the neutral axis. So for anything which is symmetric about the horizontal, will have its neutral axis right in the middle. But here it's not exactly in the middle. You can see 68.3, which is, well, what's the height? It's 80 plus, so it's 100. 100 minus 68.3 is 32 something, right? So this height is 32. So it's not exactly in the middle, my bad. It's not in the middle because the shape, the horizontal shape on top is not the same size as the one below. And so if you use the formula which we did last time, right, how do you find the centroid? You'll find that you will get C to be not in the middle. Okay, so we need to find the distance of C from the center of the top piece. This distance. So we can see that this is 10. And then we only need to find this distance if you can. $21.7. See, so I was thinking of, this is 20, so I was thinking of using this height. This is 68.3 minus 20. So it's 48.3. And this height is 80. So 80 minus 48.3. 31.7. Did you say 31? My bad. 31.7. So this height is 31.7, but to that I need to add another 10 because this midpoint is this 20 mm thick, so it should be 10. So I'll just redraw that in the other figure. It's very clear. This height we computed is 31.7, and this distance is 10. And so this is where y is. So y bar and then I need the dimension. So 100 is the length and 20 is the height. Hundred is 20. So we have 41.7. I need to convert that to meters. So 10 raised to -3. And then cross-section area is 100. 100 mm is also 0.1. And then 20 is also equal to 0.02 meters. So this comes out to be 83.4 times 10 raised to -6 meters. So it'll be meter cube because there's meter and meter square. Okay, so we got Q. Now we need to compute B. Now there is two options we have for B. So if you look at this, this is, I believe, 20 mm. So the length, this is 100 mm, and then this section is 20 mm. So 20 mm, that's 100 mm. Okay, so 100 mm because it's right here. This piece is 20 mm, that is the joint, but then immediately after the joint, there's a 100 mm width, right? So you could choose 100, you could choose 20. Which of them is a good choice? Which would you choose? So you look at the formula, where is the stress going to be maximum? Is it when B is maximum or when B is minimum? That's the B is minimum, right? If B is 20, you would have a greater stress than if you put 100 because B is inversely proportional to tau. So wherever the section is smaller, you see a higher stress being developed. So you want to put 20 mm, not 100 mm. It said the two choices, 100 mm for this one and 20 mm for here. So B is 20 mm.
So we always choose the smaller value?
Yes. Okay, so I got all the things. Let's just write the final answer. Tau equals V, which was 1.5 times 10 raised to 3. Q was 83.4 times 10 raised to -6. I is given to us. It is 8.63 times 10 raised to -6. And then B was 20 mm, which is 0.02 meters. So subbing in those values, you get tau equals 725 kPa. Yes. Yeah. V is positive actually. So if you see it's positive. Our convention is positive is downwards. Now, if the shear force was in fact negative, it just means that the shear stress direction is reversed, and it has really no consequence over here. So even if V was negative, you would just go ahead and put a negative sign. That's not a problem. It just says that shear force will be the other way. Okay, so the other part, the other question is as simple as the first one. Once we figured the first one, the second one is just so we want to find the stress at B. So we need to do the same things, which is we know the shear force at NN, which is still 1.5 kilonewtons. We only need to figure out Q and B because I is given to us. Let's quickly do that. And we are done. So now the bottom piece of the beam. Joint P. We need to find this Y bar and then the cross section. It's in the middle, yeah. So this is shown as 60 mm. This width is 20 mm. And then we need to find Y bar, which you can calculate that just like we did previously. Just going to put the value there. So I get 0.0583. And same as B, we have two choices. We choose the smaller one. So tau at B average is B, Q is the IB, B is 1.5, Q is A times Y bar, A is 0.06, 0.02, 0.0583, comes out to be 70 times 10 raised to negative 6. So Q is 70 times 10 raised to negative 6. I is given to us, it's 8.63 times 10 raised to negative 6. And B, as I said, has to be the lower of the two dimensions. Here it's either 20 mm for the thickness or 60 mm. We choose the smaller one. So that comes out to be 608 kP.